Hi everyone. In this session I'm going to be looking at the sampling distribution for X bar, and we'll start off by looking at what you need to be familiar with. For the session you need to be familiar with the normal distribution, and you also need to be familiar with the standard normal distribution, or in other words z-scores, and the standard normal table. Right, let's start with an example. Suppose that we have the following population: 1, 3, 4, 6 and 7. Now, because this is a population, the expected value, or the population mean mu, will be 4.2, and the population variance, denoted by sigma squared, will be 4.56. Now let's suppose that we select all possible samples of size 1 from this population, and of course sampling will be with replacement. So the number of samples of size 1 that we can select, we will calculate by taking population size combination sample size, and that's 5 combination 1, which of course is just equal to 5. So if this is my population, where I have 1, 3, 4, 6 and 7, all possible samples of size 1, there's 5 of them, and it's just going to be the individual values. So 1, this one over here, that's going to be my first sample, this is my second sample, third sample, fourth sample, fifth sample. Right, next we'll look at selecting all possible samples of size 2. Now the number of samples of size 2 that we can select will be n combination n, where the first n, the capital N, will of course be population size, lowercase n will be sample size, so it's 5 combination 2, which is 10. So there's 10 samples of size 2. So here we can have, for example, 1 and 3, we can have 1 and 4, 1 and 6, 1 and 7. Then we can have 3 and 4, 3 and 6, 3 and 7, etc., right up to 6 and 7. So this is all possible samples of size 2. Next we look at all possible samples of size 3. So the number of samples we can select will of course be 5 combination 3, which is also 10. So if we look at all possible samples of size 3, then we'll have 134, 136, 137, 146, all the way up to 467. And then lastly, selecting all possible samples of size 4. So the number of samples of size 4 that we can select will be 5 combination 4, and of course that will just be 5. So the samples that we'll have will be 1, 3, 4 and 6, or we can have 1, 3, 4 and 7, 1, 3, 6, 7, etc., all the way to 3, 4, 6, 7. Right, now if we take each one of these, okay, each sample now, for the different sample sizes, and we calculate the average for each sample, then this is what we're going to get. For all the samples of size 1, of course the average will just be equal to the actual observation, because we don't have more than 1, so the average is just the actual value. So here we have the value 4, so the average will be 4. Here we have the value 6, so the average will be 6, and the same for 7. So if we plot this on our x-axis, but in this case it's going to be an x bar axis, okay, because I'm interested in plotting the averages, not the actual observations, then we can see where these values are. Because they're just the observations, they're going to be at 1, 3, 4, 6 and 7. If we look at the next one, we calculate the average for every possible sample of size 2. So that means we'll take the first sample of size 2, which is 1 and 3, and we'll calculate the average, and that's 2. Next one, 1 and 4, calculate the average, and that'll be 2.5. Then 1 and 6, calculate the average, that'll be 3.5. And we do that for each one. And we plot that on our dot plot, then it's going to be the yellow dots. Now, what you should notice from this is that the range for the yellow averages is a bit smaller than the range for the purple averages. And there's a good reason for this. What happens when we have single observations is that the samples have nothing in common. So here we have a 1, and separately a 3, separately a 4, separately a 6, and separately a 7. Here we have 1 and 3, 1 and 4. So that means 1 is being shared between 1 and 3, 1 and 4, 1 and 6, 1 and 7. So because 1 is being shared over here, it automatically draws the averages for these samples closer together. If we look over here, we have 3 and 4, we have 3 and 6, 3 and 7, we have 1 and 3. So all of those contain a 3, so automatically it draws the averages closer together. And the other reason, because we're increasing the sample size, we are actually selecting more and more values from our population. Now the population mean, which is 4.2, is calculated using all 5 of these observations. So if we have a very small sample of size 1, we don't expect the sample average to be close, well necessarily close to 4.2. But the more elements we have in our sample, of course it means that our sample becomes like the population, so we expect the sample average or the sample averages to be closer to 4.2, which is the population mean. So let's see whether that is in fact the case. If we look at samples of size 3, then the first average is 2.7 and the last one here is 5.7. So if we plot those, then we get this interval. So we can see here that the interval for a sample of size 3 is already much smaller than the interval for a sample of size 1 and even a sample of size 2. And these values, these averages, seem to be converging to a specific point, which, as I said earlier, is the population expected value, which is 4.2, because we're selecting more and more population elements into our sample, so the sample values, or the sample averages rather, should become more and more like the population average. If we take the last one, which are samples of size 4, then we see that the range of averages is in fact very small. It is much smaller than the ones. Right, now our focus will be on the averages. So I'm going to get rid of the actual samples and we'll just leave the averages behind. Now if we take the first set of averages over here and we calculate the expected value for this population, okay, this is a population of averages because it's all possible averages for all samples of size 1. So the expected value for this population is 4.2 and the variance for that population is 4.56. You'll notice that 4.2 is the same as the population average or expected value, and 4.56 is the same as the population variance. Okay, the original population, whereas this is the population of averages. If we take the second one, so here, the yellow ones, we have a population of averages, and the reason why it's a population of averages is because we selected all possible samples of size 2 and then we calculated the average for each of those samples. So because we have all possible averages, it means that we have a population. So if we calculate the expected value for our population of means, okay, population of means, we see that it is again 4.2 and the variance in this case is 2.28. So the mean stays the same as what it was before, which is the same as the population, but we notice that the actual population variance is 4.56. Samples of size 1 have a variance of 4.56 as well. Samples of size 2 have a variance of 2.28. Now this is exactly what we saw in our dot plot, and we'll get to that in a moment. If we consider all possible samples of size 3, then what do we see? If we calculate the expected value of the averages, it's 4.2, which is the same as all the others. And what do you notice about the variances? The variance for this population of averages is now even smaller than before. It's 1.52. And then lastly, where we have all possible samples of size 4, calculating all the averages, the expected value for those averages is 4.2, which is the same as the others, and the same as the actual population expected value, and the variance is even smaller for this population of averages. So what we see here is exactly what the dot plot demonstrates. All of these points are averages, but for different sample sizes. As the sample sizes increase, we see that the averages converge to a specific point. That point will be this 4.2, which is going to be over there somewhere. Okay, so all the averages converge to 4.2, and the reason for that is because our samples become bigger, which means we're selecting more population elements for our sample, which of course means that the population mean is going to become closer and closer to, or rather the sample means will become closer and closer to 4.2. If we look at the spread for samples of size 1 is very big. In fact, the spread for samples of size 1 is the same as the original population, but as the sample sizes increase, the spread decreases. Okay, as the sample sizes increase, the spread of the averages decreases. Now, because we're working with all possible samples, these will be all possible averages for different samples of size n. We'll call these the sampling distributions of x bar for different sample sizes. Okay, sampling distribution, because if we take all the samples of size 4, we calculate the expected values, then we have a population of averages, so we can see the distribution of all the different averages. If we take all possible samples of size 3, then we calculate all possible averages for samples of size 3, then again we have a population of averages. So here we can see how the sample averages are distributed. So we have a sampling distribution of the averages, that x bar. The same for samples of size 2. Calculate the means for all possible samples. So because we have all possible samples and the means for them, we have a population of means. We can see how the means are distributed. So we have a sampling distribution of x bar. Right, so these are called sampling distributions for the different ends, and these will be the parameters. So for the sampling distribution of x bar for n equal to 4, we have a population mean of 4.2, and we have this population variance. Okay, so these will be the parameters of x bar. Now, let's have a look at a generalization of the results. If we consider all possible samples of size n, and we calculate all the averages, then we'll have a population of averages. And we saw from over here that if we calculate the expected value for all of those averages, it is simply equal to the original population expected value. If we look at the variance, then the variance of all these x bars is not equal to the original population variance, but it is equal to the population variance divided by sample size. As I illustrated over here, the variance for the averages becomes smaller and smaller as n increases. This was n equal to 1, and this was n equal to 4. So sample size increases and the variance decreases, and the reason we can see again in our dot plot, if we go back for a moment, in our dot plot we can see over here the spread decreases as the sample size increases. Right, so that means that the variance for the populations decreases, and the variance then is calculated by taking sigma square over n. Now lastly, what we call the shape. If the population, which we denote by x, if that population is normally distributed, and we calculate the averages for all possible samples of size n, and we plot the averages and we look at the distribution of those x bars, then it's also going to be normal regardless of what the sample size is. But in this case it's going to be normal with the same average as the population. However, from here we know that the variance is dependent on the sample size. In other words, the bigger the sample, the smaller the variance becomes. In other words, the smaller the spread. Now, next, what happens if the population is not normally distributed? Well, then we can still get a normal distribution for our x bars, or rather an approximate normal distribution for our x bars, but only for large samples. Now in statistics, we consider samples of size 30 or more as large. Right, now, some new terminology. This sigma square over n, although it is the variance, although it is the variance for the x bars, and when we take the square root of this, it will be the standard deviation of the x bars. It is also called the standard error. And there's a reason for that, which we'll see in a later session. Right, so sigma over square root of n is the standard deviation of x bar, of the averages, but it's also called the standard error. And this last result over here, which says that even if we have a population that is not normally distributed, but we select samples greater than or equal to 30, then if we plot all of the sample averages it's going to be approximately normally distributed with mean mu, which is the same as that mu from the population, but of course the variance depended on the sample size. In other words, the bigger the sample, the smaller the spread, so it's sigma square over n. And we call this result the central limit theorem. Now, as a demonstration of the central limit theorem, let's consider this population. Now, this population has a mean mu and a variance of sigma squared. It is clearly not normally distributed. It is heavily skewed to the right. In other words, positively skewed. We have this peak on the left and we have this long tail on the right hand side. So this curve is the distribution of x. Okay, this is how the x is distributed. It doesn't have a name, it's not normally distributed or anything like that. We're simply considering the distribution of x. That's it. And it has a mean of mu and a variance sigma squared. If we consider all possible samples of size 4, okay, so from that population, the black curve over here, we consider all possible samples of size 4, like what we did in the previous example, and we calculate the average for every single sample of size 4, and we plot the averages. It's going to be this blue curve over here, where the minimum x bar is going to be over there, and the maximum x bar is going to be over there. So what do we notice? Well, for a sample of size 4, when we plot the averages, it is definitely not normally distributed, okay, for a sample of size 4. But we can see that something is busy happening over here. If we consider all possible samples of size 8, and we calculate the average for each one of those samples, and we plot them in our curve, then we see that the minimum is over here, the maximum is over there. It's a bit narrower than the previous one, and we can see that these two peaks are moving towards each other. This curve is becoming smoother, but it's still not normally distributed, and it's still slightly skewed to the right. But it's definitely not normally distributed. If we consider all possible samples of size 16, then the minimum and maximum x is even closer together. It moves closer towards this middle point over here, which is the population mean, and this curve is becoming increasingly smooth. So it's starting to look almost like a normal distribution. If we consider all possible samples of size 32, then it is really very close to a normal distribution, and we see that the peak over here is at the middle point. And where is that middle point? It is the same as the population mean. Remember, this blue curve is constructed by taking all the sample averages. So if we take the expected value of the sample averages, then we get mu, which is the population mean. It's the same as that one over there. Okay, that's the middle point, and we can see that's what they're heading towards. But we can see this curve is still slightly skewed to the right. If we take all possible samples of size 64 and we do exactly the same, we see that this is becoming increasingly normal now. And if we take all possible samples of size 128, then it basically looks as if this is actually normally distributed. It's going to have a mean of mu, and it's going to have a variance of sigma square over n. Because remember what we saw earlier on, the spread, as the sample size increases, the minimum x value moved towards the mean, the maximum x value moved towards the mean as well. So that means the variance of the x bars decreases as the sample size increases. Right, let's have a look at an example with some numbers. Now it says here, an electrical firm manufactures light bulbs that have a length of life in hours that's approximately normal, with parameters 800 and 1600. Calculate the probability that a random sample of size 16 bulbs will have an average life of less than 785 hours. So let's highlight a few keywords over here. First of all, we have a population that's approximately normally distributed. We have a sample of size 16, and the interest is in the average life. So that means we're not calculating a probability for x in this case. We're calculating a probability for the average. But before we get to that, let's just illustrate this information. Right. From our previous result that we just saw a moment ago, the central limit theorem, it says that if we have a population that is normally distributed and we calculate all the possible x bars from all possible samples of size 16 and we plot those x bars, it's going to be a normal curve, and the distribution of the x bar, okay, you can see here my axis now is x bar because it's an axis of averages. So the distribution of x bar is going to be normal. The mean is going to be the same as the population mean 800, but the variance is going to be the population variance of 1600 divided by 16, because remember the variance for x bar is dependent on sample size. The bigger the sample, the smaller the spread of the means. In other words, the closer the means become together. So that means the variance or the spread of the means must decrease as the sample size increases. Right, now what are we interested in here? We're interested of the average life being less than 785 hours. So that means 785, which is less than 800, so it's going to be to the left. If we indicate here the cutoff point for 785, then we're interested in this blue area over here. Right, so in terms of our notation, we're interested in the probability of the average, in other words, the probability of x bar being less than 785. Okay, so let's write that, probability of x bar being less than 785. Now, what did we do before? When we were interested in calculating the probability of a single observation, then this was just x. And the procedure was to determine how many standard deviations is this x away from the mean. So that's exactly what we're going to do over here. We're going to determine how many standard deviations is x bar 785 away from the mean. Okay, how many standard deviations is 785 away from 800? So we'll calculate our z-score, because z-score is the number of standard deviations. So the formula for calculating a z-score is x minus mu over the standard deviation. But in this case, we're not interested in a single value x, we're interested in an average. So we'll have x bar minus mu. And because we're working with x bar, we're not working with the standard deviation of the population, which will be the square root of 1600. We're interested in the standard deviation of x bar, which is what we get over here on the right hand side. So it will be the square root of 1600 over 16. Right, so what do we have? 785 minus 800, which is the difference between these two. Sigma is 40. Remember, 1600, that is sigma squared, so the square root of that is 40. Then we divide it by the square root of n. N is equal to 16, so the square root of 16, that is equal to 4, and that's where this 4 comes from. So if we rewrite that, simplify, then we get negative 1.5. So that means that the probability of the average being less than 785 is the same as the probability of the z-score being less than negative 1.5. In other words, being below this 0.785 is the same as being further away than 1.5 standard deviations from the mean. Now, we need to go to our z-table for this. We have a z-score of negative 1.5. Remember, the z-table has the z-score split into two parts. The first column we have the integer and the first decimal, and then in the top row we have second and third decimal. So here we have negative 1.5, so we simply look for negative 1.5 in the first column, and then 0, 0, 0, 0 in the first row, and of course where they intersect we will have our probability. Now remember, this is less than, in other words, it's a cumulative probability, and we're lucky because the table gives us cumulative probabilities, so we can simply use the 0.0668 as it is. So that means taking the 0.0668, it is just 6.68%. So if we go back to our graph, then this blue area here has a size of 6.68% or 0.0668, and our conclusion will be that there is a 6.68% chance that a random sample of size 16 will have an average life of at most 785 hours.